Hello friends, MoNaCo here, our seventh and second to last video in our moles and stoichiometry unit. We're talking about empirical formulas today, and you're going to need two things in order to do this work properly. Calculator, periodic table that has the atomic mass of the elements on it. So what we're going to be able to do today is we're going to determine the empirical formula for any compound. The question you might have is, what's an empirical formula? Well, simply put, not all compounds are in their simplest forms. And an empirical formula is the simplest form of a compound. It represents the smallest whole number ratio of atoms of one type to atoms of another type in a certain compound. They're different than the molecular formulas, but they are simpler. So an empirical formula, reduced formula, it's a formula whose subscripts cannot be reduced any further. Basically, the subscripts of all the numbers of the elements in the formula are already in their lowest common factor. A molecular formula is more representative of what the actual compound is. Subscripts represent actual quantity of atoms present. Why do these things exist? Well, originally we used the empirical formula to figure out the molecular formula using the masses and moles of the chemicals elements that are involved. So it's kind of a really involved process. Elemental empirical analysis is what was done many, many years ago to figure out the chemical formulas of these compounds that we see every day. So you say C6H12O6 or N2O4. How did they figure that out? Well, they did this long involved process called empirical analysis and figured out the chemical formulas that we know today using the mass of the elements in very convoluted ways, but I'm going to show you a little of that today. So the molecular formula here on the left is the actual number of atoms present in the compound. The empirical formula is when you reduce that. So if you see here, the ratio of nitrogen to oxygen is 2 to 4. So this is really a 2 to 4 ratio, which we can reduce down to a 1 to 2 ratio. So the empirical formula would be N1O2 or NO2. It's just that simple. You break down the molecular formula into the empirical formula going in one way. C3H9, this is a 3 to 9 ratio, which is the same as a 1 to 3 ratio. So C1H3 or CH3. Now, if you think about that, CH3 itself, carbon with 3 hydrogens around it. From our previous unit on bonding, we know that carbon's missing a bond there, which is why an empirical formula isn't true to what the elements are and how they're connected. It's the simplest form, okay? So let's look at this, C6H12O6. This is a 6 to 12 to 6 ratio, which you can reduce because there's a common factor there, the number 6. If you divide every subscript by 6 there, you get to the ratio of 1 to 2 to 1. So we get CH2O, which again, if we were to try and draw a Lewis dot structure or something like that, it wouldn't really make that much sense. Okay? B4H10. This is a 4 to 10 ratio. What would the formula be? I want to see you figure that out when you do your homework check. A 5 to 12 ratio. 5 to 12. Can we reduce that at all? It cannot be reduced. You can't. There's no common factor between 5 and 12, so it's C5H12. Sometimes the molecular formula is the empirical formula. It all depends on the ratio of the elements. Okay. Now, there's some more examples I want you to do. Don't panic when you see a parentheses. Basically, this means that there's a 1 to 3 ratio between the iron and the carbon monoxide. Okay, so that's what it is. So it's already in its lowest common factor. So if you see a parentheses, don't panic. It just means we're talking about that polyatomic ion. Now, if you're asked to do the other thing, convert an empirical formula from its percent mass, it's a 3-step process. First step is you always assume you have a 100-gram sample because your percentages can be turned into grams really easy by just changing the units. We're going to convert grams to moles using that mole conversion calculation from table T. And then we're going to divide all the mole numbers by the smallest mole number to get the formula for the empirical compound, the empirical formula. So here's an example of what you might see. A compound's 46.2% by mass carbon and 53.8% by mass nitrogen. What is its empirical formula? So step one, we assume everything's a 100-gram sample, which means 46.2% carbon's 46.2 grams carbon. We just change the percent to a gram sign. It makes it really easy. Step two is a little tough because we got to use our calculator and our periodic table to get those grams into moles. So moles carbon is going to be equal to 46.2 grams divided by 12 grams per mole. That is the atomic mass from the periodic table. So 46.2 divided by 12, 46.2 divided by 12, that's 3.85 moles of carbon. The other element in there is nitrogen, so we have moles nitrogen, and that's going to equal 53.8 grams divided by nitrogen's atomic mass, which is 14 for ease of calculations, grams per mole. And that's going to equal 53.8 divided by 14, 3.84. 0.84 moles nitrogen. So now we got to go to the third step, which is divide all the numbers by the smallest number of moles. So divide each mole number by the smallest mole number. We will round in this step to the nearest integer if it's super close. So if we check here, 3.85 divided by 3.84, it's pretty much the same thing. So for carbon, we got a 3.85 mole divided by, well, 3.85 mole. That equals 1. And for nitrogen, it was 3.84, which, well, might as well just divide it by 3.84 because it's the smallest. I mean, this, for all intents and purposes, as long as it's the same, it was just my rounding in the calculator that was different. That equals 1. So we have 1 mole carbon, 1 mole nitrogen. That's the basic ratio of carbon and nitrogen. So the formula is N1. It's a 1-to-1 ratio. Now, there's many more ways to do this. Well, not ways to do it, but there's many more practice calculations. Again, the first step is convert your percents to grams, which has already been done for you. Calculate the empirical formula. So we're starting with step 2 in this case. We're going to divide 24 grams of carbon divided by 12 grams per mole. That equals blank moles of carbon. I want to see that calculation in your homework check. And then we'll do the same thing for oxygen. 32 grams of oxygen divided by 16 grams per mole equals blank moles of oxygen. So then, of those two numbers, remember you got to do step 3. We have to go through step 3 to find out the actual lowest ratio. So I want to see your calculation, and the final answer here is the empirical formula. 3-step problems. Follow the process. Convert the percentages to the grams, then go with grams to moles, then divide the moles by the smallest mole number. You might start with different steps. In this case, you're going to start with step 3. So you're already going from step 1 and 2 have been done for you. So 0.5 mole carbon, and divide that by 0.5 because we're dividing by the smallest number, equals, well, that's 1 mole carbon. And for the other one, 1.0 mole hydrogen, we're going to divide that by 0.5 mole. Well, that's 2. So the ratio there, and again, I want to see the formula when you're done, is a 1-to-2 ratio. So what formula would that be? This last one, you do have to do all 3 steps. Well, I'm sorry, it's not the last one, but in 3 and 4, you got to do 1, 2, then 3. You got to do all 3 steps, and you might need extra scratch paper in order to do it. This process is involved in its multiple steps, and the only way that you're really going to get it is through practice, practice, practice. There's only a couple pages in our practice packet, so we created a very small empirical formula CASEL learning assignment to help reinforce this particular content. So thanks for watching, and be prepared to do practice on this because you got to do it every now and then on the Regents exam. Thank you.